If you're waiting for a Tesla Model 2 with solid-state batteries, 5-minute charging, and a 1,000-kilometer range, stop. That vehicle does not exist in the real world of manufacturing. From the perspective of an engineer looking at a bill of materials putting the most expensive battery technology on the planet into a $25,000 car is not innovation. It is the destruction of the cost structure. And once you look at the numbers, it becomes obvious why Tesla will never do it. What does a $25,000 car actually need from its battery in order to be mass-produced? At this price point, a vehicle is not optimized for maximum range or peak performance. It is optimized to survive mass production. In practical terms, that means the battery pack cannot exceed roughly 30 to 40% of the vehicle's total bill of materials. For a $25,000 electric car, this places a hard ceiling on battery pack, cost at approximately $3,000 to $4,000. This is not a theoretical preference. It is a financial constraint imposed by margin supplier pricing and capital expenditure realities. Lithium iron phosphate battery packs produced at scale already operate within this boundary. During the 2024-2025 period, pack-level LFP production costs in China have been widely reported in the range of $50 to $70 per kilowatt-hour. As a result, a 50 kilowatt-hour pack sufficient for roughly 250 to 300 miles of real-world urban driving can be produced within the allowable cost envelope. Millions of such packs are already in use on the road today. If LFP already meets the cost target, what exactly does solid-state technology improve for a $25,000 car? Solid-state batteries promise higher gravimetric and volumetric energy density. In theory, that is correct. But engineering decisions are not made in theory. They are made in real-world context. A mass-market electric vehicle does not require extreme energy density. It requires an appropriate balance between cost energy and usability. In practice, daily driving needs are modest, and the usable energy provided by today's LFP packs already falls within the optimal cost range. Adding additional energy density beyond that threshold does not improve the product, it increases cost. The conclusion is, straightforward excess energy density that drivers do not need is not a benefit, it is a cost penalty. This leads directly to the second critical issue, how solid-state technology impacts the cost structure of an affordable electric vehicle. Even under the most optimistic assumptions, solid-state batteries remain expensive. Public disclosures from major developers such as Toyota QuantumScape and Solid Power indicate early solid-state packs costing $400 to $800 per kilowatt-hour. Even assuming major technological breakthroughs and future cost reductions, the gap relative to LFP remains enormous. At $400 per kilowatt-hour, a 50 kilowatt-hour pack costs $20,000, nearly equal to the entire target price of the vehicle. No amount of platform optimization can close that gap. Motors, inverters, body structures, electronic safety systems, and assembly all still carry unavoidable costs. The numbers simply do not align. From an engineering management perspective, this is not a trade-off, it is an impossibility. Cost alone is sufficient to eliminate solid-state batteries from consideration for a $25,000 Tesla, but manufacturing reality reinforces this conclusion even further. LFP batteries are produced using mature lithium-ion production lines with high-throughput predictable defect rates and well-understood failure modes. These processes have been refined for over a decade. Yield losses are low enough to support high-volume, low-margin products. Solid-state batteries, by contrast, introduce new manufacturing challenges. Many architectures require extremely high material purity, precise solid-solid interfaces, and in some cases, continuous mechanical pressure to maintain ionic contact. Pilot line yields remain far below automotive requirements. Every percentage point of yield loss increases effective cost. In a vehicle designed with razor-thin margins, such variability is unacceptable. This raises an uncomfortable but necessary question: can a mass-market vehicle tolerate yield risk from an immature production process? In automotive engineering, the answer is no. Large-scale production programs are built on statistical predictability. When yields are unstable, cost forecasting collapses. That level of risk may be acceptable for low-volume luxury vehicles or aerospace applications. It is not acceptable for the cheapest car a company sells. Mechanical reliability further highlights the mismatch. Vehicles are not gentle environments. Battery packs must endure constant vibration, thermal cycling torsional loads, and impact events throughout their service life. Many solid-state designs rely on ceramic electrolytes, which are inherently brittle. Under repeated mechanical stress, microcracks can form at interfaces, increasing impedance and accelerating degradation. In some failure modes, degradation occurs abruptly rather than gradually. From an automotive reliability standpoint, this is deeply problematic. Gradual, predictable capacity fade can be managed. Sudden failure cannot. Entry-level vehicles are expected to operate reliably for many years with minimal maintenance. Introducing a chemistry with less stable mechanical behavior into the most price-sensitive product runs directly counter to that requirement. This leads to another key engineering question: why introduce higher failure risk into the lowest-cost vehicle platform? Despite its lower energy density, LFP chemistry offers strong mechanical robustness. It tolerates vibration, exhibits stable degradation behavior, and has a significantly lower risk of thermal runaway. These characteristics enable simpler thermal management systems and lower safety costs. Simpler systems cost less. In a $25,000 car, simplicity is not a compromise, it is a design objective. Supply chain considerations further constrain the choice. LFP batteries rely on iron and phosphate materials that are abundant, geographically diversified, and relatively price stable. This reduces geopolitical risk and commodity price volatility. Solid-state batteries often depend on specialized materials and proprietary processes that are not yet supported by mature global supply chains. Scaling production under such conditions introduces additional uncertainty. At this point, the final question becomes unavoidable. Why would Tesla, a company obsessed with manufacturing efficiency, risk its highest volume product on a battery technology that fails simultaneously on cost, yield, and reliability? The answer is that it would not. And historically, it does not. Tesla's pattern has been consistent. New battery technologies are introduced first, where margins are high and volumes are low. Only after the cost curve stabilizes and manufacturing reaches high yield are they pushed down into lower segments. This is how lithium-ion batteries reached the mass market. Solid-state batteries may follow a similar path, but they are not there yet. A $25,000 Tesla is not a technology demonstration. It is a mass production machine. Its success depends on building millions of units with predictable cost and performance. LFP batteries enable that today. Solid-state batteries do not. This conclusion is not ideological. It is technical. Solid-state batteries may be part of the future of electric vehicles, but they are not the solution for affordable transportation today.